Welcome everybody. As you can see, I have a bit of a situation at home, and to be honest, I haven't have time to practice my talk. So yes, I would like to apologize in advance for that. And if I'm running over 20 minutes or 20 something minutes, just yeah, please let me know. Yes. So my talk is divided in 3 parts. First, I will briefly talk about IFC, or information flow control. Then a bit about WebAssembly, or Wasm, and finally our product SecWasm. So information flow control is a language-based technique which has the goal of enforcing, or mainly enforcing, a property called noninterference. And non-interference says that if we have secret data and public secret inputs and public inputs that go into a program, then only the public inputs should influence what is output on a secret channel, and secret inputs should not have any effect on the public outputs. Non-interference is a property of traces. So how we would usually look at it is like we compare different, we look at traces of different program executions, and we see if we if we execute a program with a certain secret, and we have as a result, if we produce another secret output. And so if we have two executions in which they differ only on the secret data, but not on the public inputs, then the public outputs should be the same. So this is basically what non-interference says. And depending on the setting and on the attacker view of the system, we may be interested in the inputs, or looking at the inputs and the outputs and the relationship between them at the end of the program execution, or we may be looking at the memory locations and the values before the program has been executed and after the program has been executed. And how we enforce non-interference is by tracking flows of information. And we do this by assigning labels to variables. We assign public and secret labels, and we can have explicit flows when we directly assign a secret variable to a public one, or when we output a secret variable on a public channel. And then we have implicit flows when, depending on the value of a secret, where depending on the value of a secret, we modify public data. And we have different types of enforcement mechanisms. We can have static enforcement mechanisms, which use a security type system. Here we have a security context, which keeps track of the variables and the security labels they have. And we can have, and we can have a dynamic enforcement, where we have a program state, and we extend the program configuration with a security state. And here we monitor the program execution. And we look at the observations that we get. And these observations may be visible to the attacker. And in case these observations leak some secret data, then we abort the execution of the program. And we can also have hybrid enforcement mechanisms, and these are a combination of static enforcement with dynamic monitoring. So this was the brief introduction on IFC, and now let's look a bit at Wasm and or WebAssembly and what it brings. So in WebAssembly, we have a structured control flow and an unwinding operand stack. We have an unstructured linear memory, and we have a well-defined type system. So these are some key points that we are going to need later. The control flow is obtained. We have control flow. We have certain control statements, and the structured control flow we get by or through the use of this end instructions. We have block constructs, and we have these end statements, and we have 3 different branching instructions. So what makes the control flow to be structured is the way this the syntax of the languages or the semantics, and the fact that we have an unwinding operand stack. We can look at an example so you can get a better feeling of this. So let's assume we have the following Wasm code here, which corresponds to this C program. If x is true, then we return 0. Otherwise, we return 1. What we have here is the first instruction, which pushes the address of x on the stack. Here you will see the stack. Then we read the value of x from the memory. And now we enter a scope, which is a block. And we have by $0, we denote the label of the block. And now we add to the stack, but note that we add it on the bottom of the stack. And what we do, we see here that the block has a type which says that it takes 1 argument, which is a 32 integer, and it returns 1 value, also of type also inter 32 byte. And what the execution did to the operand stack was that before entering the block, it popped this 1 value, which was on the operand stack, pushed the label, and then finally pushed this value back on the stack. We enter the second block, so we do a similar operation. We pop this initial value, and we push the label of the block, and then we push back this value that we had earlier. This block takes 1 argument but has no return value. We continue, and the instruction on line 5 takes the first value on top of the stack, and then it checks. If it is 0, then it will put back a 1. Otherwise, it pushes value 0. And now let's assume that x was 0. In this case, we are going to push back, like we are going to pop this value and push back 1 on the stack. We continue with the next instruction, where we have a conditional branch. So here, again, we check what value we have on top of the stack. If this value is different than 0, then we are going to perform a jump out of 0, which corresponds to this value, plus 1 blocks. So we are going to perform a jump, and we are going to give control to the instruction on line 10. And note that when we now when we left the block, because we left 1 block, we are going to pop the label of that block. But because we have to return 1 value, we are going to put back on no, sorry, I got confused. Because we left this block, which has no return value, then there's nothing more happened to the stack. Instruction 10 just pushes value 0 on the stack, and finally we exit on we finish this the execution of this program by exiting the first block, which returns 1 value. So this means that we are going to pop the first value on the stack, remove the label, and then push this value back in. So this is how the evolution of the operand stack looks like for the execution of this program when x was 0. This is how the operand stack, or the evolution of the operand stack, looks like when x was not 0. We will come back to this a bit later. Now, we said that WebAssembly has a linear memory. So for working or the operations for the memory operations are the following. We have read, we have write. We can query for the size. We can query the size of the memory, and we can also dynamically grow the memory. But in this talk, we are going to look only on the read and write. So here, let's assume this is our memory of size n, and we want to store some value in this memory. So the storing operation needs two values on the stack. One is the actual value that we want to store, and the second one corresponds to the address where we start the writing in the memory. So assuming that we want to store value 10,752 on starting with position 0, then we get a new memory, which is this one. And if we want to read from the memory, starting from position 1, then we are going to read value 42. So note that in WebAssembly, we can use any two consecutive memory locations to form a value. This is going to be important for one of our design choices in SecWasm. So now that we've seen a bit of how WebAssembly looks like, and you got a brief idea what information flow control is, like how do we combine them to get SecWasm? So recall that I said earlier that noninterference is a property of traces, and that usually, depending on the setting and depending on the attacker view, we are interested in different components of the state. And in the attacker capabilities that we assume that we assume in our setting are the following: that an attacker is able to execute Wasm programs and can see the final state of global variables which have a label which is below the label of the attacker. The attacker does not observe the linear memory and does not observe the operand stack. So also recall that there were 4 key elements I mentioned about WebAssembly, that we have a structured control flow, we have unwinding operand stack, we have unstructured linear memory, and we have a well-defined type system. Now, in SecWasm, we are going to have an unstructured labeled linear memory, and we are going to have a security type system. Note that also the typing judgment has changed from the one that Wasm is using. And in addition to this, we are going to have semantic security checks. This means that our enforcement of non-interference is hybrid. So we're going to have both static security checks through the type system and also dynamic ones through the semantics. And yes, there's a small note on the slide. We are using a big step semantics in our formalization, which is in contrast to the small step semantics that WebAssembly uses in their documentation. So how does this labeled linear memory looks like? So every memory location receives a security label. And because of this, both reading and writing instructions are also adorned with a security label. And we employ dynamic checks when reading from the memory. So let's say now that we want to read, we have the memory here on the slide, and we want to read the value which starts at position 1. We are reading a 32-bit integer, so we are going to read 4 from 4 locations, but we want to read a low value. And we note that here on the 4th location, we have stored, or there is already stored, some bytes from medium labeled value. So during the execution of this program, or the execution of this program is going to crash, because the security checks here are not going to be medium. Security label medium is not below L, so this is not going to go forward. But if we are trying to read a value of security label high, then this program is going to be is going to execute successfully. For writing a value in the memory, we have static checks. So if we want to store a high labeled value on if you on position 2, or if you want to store value 2 on position 2, and we want to this value to have sensitivity to high sensitivity, then we type check this before we execute the program, and then we check. We have this long constraint that we have to check, and if this is satisfied, then we can execute the program, and this will always writing will always succeed. And writing also overwrites. So we have a flow sensitive memory labeling. So when we write, we also update the labels in the memory. So assuming that we had this labeling of the memory prior to executing this program, then at the end we are going to have this new memory labeling. This is a brief summary of what changes we have in the memory. So we employ dynamic security checks when we read, we have static security checks when we write, and we have flow sensitive memory labeling. Now, wait. Yes. Let's go back to this example that we've seen with the two with the sorry with the two okay, we've seen this example, and depending on whether x was 0 or not, we can have different evolution. We can have different evolutions of the operand stack. Now, if we assume that the value x was secret, was high labeled value, then how would we deal with the implicit information flows, or how would we track the flows in Wasm? So first, for tracking the explicit flows, we use a stack of security labels, and we assign one security label to every element on the operand stack. And for tracking the implicit flows, we use a stack of PCs, or also it's a stack of security labels. So recall that or I'm not sure if I mentioned that, but in Wasm, we have blocks, and these blocks can only be nested, and we can jump out of these blocks in any way, depending on what branching instructions we have inside. And because we have these nested blocks, we are going to use one PC for every block. So that's why we get at the end a stack of PCs. And finally, we combine the stack of security labels for tracking the explicit flows with the stack of PCs, and we get like a stack of stacks, which are going to use in our typing judgment. And if we go back to this example and we see how the labels would be assigned to the values on the operand stack, so this would be the following. Here in red, we see the program on the left, and these values are going to be executed in a high context. And on the right, we see how the values of the type stack or label stack are going to also change during the typing of this program, and they also become secret. So recall that this was the attacker model, or these were the capabilities of the attacker. And I said that the attacker is not able to observe the linear memory, and the attacker is not able to observe the values of the operand stack. However, when we want to prove non-interference, we need to make certain judgments, and about the values that we are working with, and we need to, usually these proofs are by induction, and for the inductive invariant to go through, we need to make some statements about the linear memory and the operand stack in different executions of the program. So this means that in our statements, we have to take them into account, and we have to relate them to the attacker, and we have to say, okay, we have to assume that the attacker observes some information about them, although in reality, the attacker does not. So what this means is that when we want to prove confinement is a property which relates the program state before entering a high context and after leaving a high context. And we have a relation which relates the operand stack before entering the high context and after entering the high context. And then we have an equivalence relation between the operand stacks in two executions at roughly the same point. And this is a very abstract view of how these equivalence relations work and how we prove non-interference. Here we show, I show the statements of confinement and non-interference. And with this, I get to the end of my talk. We designed SecWasm, which is a hybrid information flow control enforcement for WebAssembly. We use a fine-grained flow-sensitive memory labeling. We augment the type system of WebAssembly with security checks. We also employ some dynamic checks, and we finally prove that SecWasm enforces termination-insensitive non-interference. Thank you.
Thanks a lot for the lovely talk. Time for questions. Yes. Okay, that's working.
I don't think it's working.
How do we check that? Maybe you can come here and use the microphone. Or...
Okay, it's working now.
Working now.
Nice talk, and well done taking care of your baby while you were giving the talk. I wonder if you considered using the multi-memory model of Wasm in order to isolate PCs that should not actually interfere.
Okay,
so
but
not using a single linear memory model, but basically having separate mappings that can have different properties.
I think there was the SecWasm work does this, right? They use they have one memory for one security level, but we thought we are more flexible if we do it this way. We get more flexibility. Because let's say that, yeah.
Can you elaborate?
Yes, so if you have, for example, objects which have attributes like secret attributes and public attributes, and then when you compile down to Wasm, then these attributes would have to be split into different memories. Or if you have an array and certain elements of this array are going to be private and others public, then when you compile down to Wasm, then they have to be split. So it's less, flexible if we have different memories.
Thanks.
Other questions?
Hello, thanks for the talk. This
Yes.
was my first connection to WebAssembly, so this question might be dumb, but since we don't have many, I will just go for it. So I was thinking about the dynamic checks you do, and I'm not sure whether WebAssembly is targeted by side channel attacks, but could you implement some kind of history to like check timing behavior of accessing high level variables and therefore terminate the execution whenever you think or seem to detect like a timing attack behavior? I mean, this is a hard question, right?
So to have some kind of a counter or like.
Yes, so I was thinking that when you detect like operating on high level variables, you could track some kind of counter timing behavior for how long you spent in the execution. And then I mean, you had to keep this information somewhere in the memory. And when the block is called again, you could check against that. I'm
Okay.
actually not sure.
Yes, but then I'm not sure if this will work because of the way they have this unstructured memory. So maybe you can overwrite that part. I'm not sure. We did not look into that.
Yeah, sure, fine.
But I don't know if you can reserve parts of the memory for storing this counter. I'm not sure. Sorry.
Any other question? In that case, I can ask a question myself. So you have a slide on your attacker model.
Yes.
Can you explain a bit like the motivation behind this particular choice of attacker and what is the kind of real world scenario that you're guarding against?
So we found this to be realistic. And this is true, like you don't have access to the operand stack and you don't see the linear memory. And what we thought was like assuming that you have like a password meter website, and then this communicates with some under another third-party website, like to fetch a password dictionary or something, and then like the password meter will fetch the dictionary in the background, and like you would make sure that this communication with the third party is going to happen securely. You're not going to leak any information there. So this was like our assumption.
So the unobservability of the linear memory and operand stack is enforced by the VM already?
Yes.
Okay. Guess we have 1 more minute, so I can ask one more question while the next speaker takes the stage. How difficult is it to implement the dynamic checks? I mean, the beauty of a completely static system is that you don't need to modify the VM.
Okay, so this is an easy question to answer. We have no implementation. So our work is unfortunately at the moment only theoretical. We have no implementation, so we cannot talk about overheads, about anything. But I'm hoping for the future to have an answer there too.
Great. Okay, thanks a lot.